Hi everyone, and welcome to your video for Experimental Methods Part 1. So last week we talked about hypothesis testing in general as a five-step process, and this week we're going to be talking about how we do that five-step process specifically for experimental methods, and even more specifically for a certain type of experimental method. Last week we talked really briefly about selecting statistical tests, and we talked about how deciding which statistical test we use is a function of what kind of variables we have for both the dependent and independent variables, and then what kind of information we have about the population, and then the numbers of levels of a variable. This is the decision tree that we looked at last week, but we only really touched on it briefly, so let's spend a little more time with it now. So the first question is whether our dependent variable, or our criterion variable, is continuous or categorical. And so let's go to the right first. If it's categorical, that means we're predicting an outcome that occurs in groups. Something like, say if we were trying to predict the likelihood of students dropping out, that would be a categorical dependent variable. And we're not going to talk about any of the kinds of tests for that kind of outcome. They're a little too complex for the level we're at here. They're not that uncommon in education, though. Dropout, as an example, is something that people are really interested in and look at often. So you may very well read papers that include a lot of these things like nonparametrics. Those are things like chi-squareds and Mann-Whitney tests. And then you may also see people do things like logistical regression. But we're not going to go into the details regarding how to do them. So for now, let's just get rid of them. And then next, so now we're down to the options with a continuous dependent variable. And then our next question is whether our independent or predictor variable is categorical or continuous. And let's go to the right again, and as you can see, if it's a continuous variable, we're going to do a regression, or alternately, we may do some other kind of correlational technique, which we're going to talk a lot more about in a couple of weeks, because these are primarily used for non-experimental studies. So let's get rid of them too for now, and then remember that we're going to pick them back up in a couple of weeks. Okay, so now we're back down to the options where there is a continuous dependent variable and a categorical independent variable. And this is generally where experimental methods live. And the next question we need to ask is what we know about the population. As we discussed last week, the whole principle of hypothesis testing is determining how likely it is that our sample came from the null hypothesis population. So a lot of our tests depend on knowing something about the null hypothesis population. Last week we looked at the case in which we know both the population mean and standard deviation. That was here when we did z-test. But most of the time we don't know these things. In particular, the population standard deviation is something that we really know very rarely. It's only for a certain kind of tests that have gone through a development system called population norming. So IQ tests, SAT tests in the US, of course, EQAO actually I think is population normed. And all that means is that they've established what the population is. And since they've established that, they can tell us what the standard deviation of that population is. But most of the time, unless we're doing one of those tests, we just don't know that. Now, there's a quick caveat here. Some statisticians argue that if you have a high enough sample size and the population mean, then you can do a z-test on that data. So even though you don't have the population standard deviation, if you have a sample size of 200 is a number that they throw around sometimes, then that counts functionally. Your sample size is big enough that the sample standard deviation should functionally be the same as the population standard deviation. And then you can use the sample standard deviation as the population standard deviation. I personally disagree with that view. I think you either have the population standard deviation or you don't, and I don't like the idea of using a sample one, even if you have a really high sample size. I'm only mentioning this because some textbooks will say to use a z-test if you have the population mean and a really high sample size, whether or not you have the population standard deviation, and I just really, really disagree with that. So if you happen to see that in a textbook, it's not a mistake either on their part or on mine. It's just a difference of opinion about how statistics should work. Anyway, this week we're talking about scenarios in which we don't know the population standard deviation, which is, as I mentioned, most scenarios. So for now, let's just ditch the z-test too. So that brings us down to what we're going to be discussing this week and next week, a category of tests for which we're comparing categorical independent variables and we don't know the population standard deviation. Now this group we're going to split between this week and next week. This week we're going to be looking at a family of tests where we're comparing two things. That's these folks here. In the case that we know the population mean, we're comparing our sample mean to the population mean. So we're comparing two things. And then in the case that we have two groups, that's comparing two groups. And then later I'll talk about another situation where we're comparing two time points or two related groups. And as you can probably already tell here, all of these scenarios are covered by a family of tests called the t-tests.
Picture me upon your knee with T for two and two for tea. Just me for you and you for me alone.
So yes, as Doris Day says, t-tests are for two. T is for two. All the t-tests that we're going to talk about are very similar, which is why we're discussing them together. And the main thing to remember is that they compare two things. They are for two. So hopefully you remember a couple of weeks ago we talked about the sampling distribution and how we could calculate the standard deviation of the sampling distribution for the null hypothesis using the population standard deviation, and then that would give us the average amount of sampling error for samples that come from of this size from a certain population. And then we could use that to say the probability that our sample would have come from that population. And if it was low, then we could reject the null hypothesis and provide support for the research hypothesis. The problem with not knowing the standard deviation of the population is that we don't know the exact shape of this curve. It's still a sampling distribution, so we know it's likely to be normal, but we don't know exactly how it's normal. And if we don't know that, it's hard to figure out the exact point on the curve that our sample would be at. And if we can't figure out the point on the curve, then we can't figure out the probability of being at that point on the curve. So what do? Well, our only option here is to estimate the size of the population standard deviation by using the sample standard deviation. Now, the problem with using a sample standard deviation to estimate the population standard deviation is that our sample standard deviation is limited by the fact that it's a sample. We talked a little bit about degrees of freedom last week, but to recap, the amount that our sample can vary is limited by the number of participants in each sample. Typically, the degrees of freedom is the total sample minus 1, because one instance is always going to be determined by the others. By the way, that's a theoretical thing, just to clarify. It's not like you test 30 people and then one person just doesn't fill anything out. It just means theoretically only 29 of those people can fluctuate. But anyway, so because variability is limited, the standard deviation that we estimate from the sample can't ever truly mimic the sampling distribution that we could get if we had the population standard deviation. But the good news is, it's wrong in ways that are predictable. So let's take a look at the image here. This is what's called the t-distribution. On the right, where it says k, they're using k here to mean degrees of freedom. So we can see for every sample size you could have, your curve is slightly different based on how truncated your variability would be based on that sample size. The pink curve you can see here is k equals infinity, or degrees of freedom of infinity, which means if you tested every single person in your population, that would be the curve that you would expect for your sampling distribution. Now, of course, if you tested every single person in the population, then by definition, your sample standard deviation and population standard deviation would be exactly the same, right? So the pink curve is actually the exact same as the curve we used last week for the z-test. It's the standard normal distribution, or the z-distribution, or whatever you want to call it. But if you have, say, only 6 people in your sample, so degrees of freedom of 5, that's the green curve. And then no matter what mean and standard deviation we actually find in our sample, it's going to approximate that shape, just a little more truncated than that perfect pink one. So if you have a sample of 11 people, so degrees of freedom of 10, you're looking at that yellow line, which you can see is in between the green and pink ones, which is basically how it goes. The larger sample you have, the more degrees of freedom you have, the closer you get to that pink distribution. Now, that doesn't mean that smaller sample sizes are bad here. It's actually totally fine to have a degree of freedom of 5 or 10 or whatever. The only important thing is that you know you have a degree of freedom of 5 or 10 or whatever, so you can see which curve you're supposed to be looking at. And then once you know that, you can figure out where your sample mean lies along that curve, and then you can figure out the probability of being there. So the logic of the t-test is like all other tests in that it's going to be a variation on signal over noise. The big difference for t-test compared to the z-test we did last week is that our noise, the standard error, is going to be based on the sample standard deviation instead of the population standard deviation. And sample standard deviation is fairly straightforward. Instead of putting the sum of squared differences over n, we're going to put it over n minus 1 to account for degrees of freedom. See, that's the only difference in the standard deviation calculation. Now remember, this is just to calculate the basic standard deviation for your sample. This isn't the standard error yet. That's going to be different for every test we do, and I'll get into that in a second. So that's the logic of t-tests, and all t-tests follow that basic logic and will be along a t-distribution, but there are some differences based on some of the other factors that we're going to have to consider as we decide which of the family of t-tests we're going to use. First, let's talk about a scenario in which we know the population mean. That's the one sample t-test. We use one sample t-test when we want to compare our mean to a known population mean, but we don't have the population standard deviation. We can also use one sample t-test when we want to compare to a theoretical mean. So if you don't know the population mean, but you want to compare to a theoretical population, you can do that. So sometimes in education, when people want to compare to zero or to chance, you can use a one sample t-test. So if I had a multiple choice test and every question had 4 options, you would have, by chance, a probability of getting 25% of them right, or 1 out of 4 chance on every question, and then for all the questions, that overall means a 25% chance. So sometimes if you want to see whether students' scores on a multiple choice test are better than what they would get by chance, instead of being, say, better than 0 or better than something else, you would want to compare your sample mean to a theoretical population standard mean of 0.25 or 25%. So it's essentially a theoretical population. So as you can see, it is very similar to the z-test, but with the bottom change, because we're using the sample standard deviation in our calculation of the standard error. So here's how you would write the equation, both in text and then in the symbolic notation. So just as a side note, if you were wondering why the sample standard deviation is over root n instead of root n minus 1 when we're going ahead and calculating the standard error, and that's because we're already accounting for degrees of freedom in the sample standard deviation. We don't need to do it twice here. We account for it in the sample standard deviation, and then we use the full n here to turn that into a standard error. So really all we're doing is using the sample standard deviation to fill in for the population standard deviation here. Let's work through a quick example using our steps of hypothesis testing. So in step 1, let's say I have a research question that I'm interested in whether kindergartners know basic facts about birds. So I draw a random-ish sample of 41 students, and I run the study in which I ask them questions about birds, and they answer yes or no. In this case, I don't have a specific population I'm comparing to, but since I'm asking yes/no questions, I want to test whether they're performing better than chance. And because the answers are yes/no, chance would be 50%, right? So I set up a null hypothesis. In this case, the null hypothesis is that there's no difference between this sample and chance. So 0.8 minus 0.5 equals 0. So then, all we have to do is take the formula we saw earlier and apply it. And you can go through all this math yourself, but it works out to t equals 12. And then moving on to step 5, we need to make our decision. So if you remember from last week, we need 4 things to make our decision. We need the alpha, whether it's 1 or 2-tailed, the degrees of freedom, and our score. And this time we actually do need degrees of freedom because we're using a t-distribution, right, instead of a z-distribution. And in our case, the alpha is going to be 0.05. It's a 2-tailed test. Our degrees of freedom is n minus 1, so that's going to be 41 minus 1, which is, of course, 40. And our t-value, as we just found, is 12. So like last week, we're going to take all that information and look it up in a table. Now, t-tables work a little bit differently from the z-tables we used last week. Because probability fluctuates based on the degrees of freedom, we don't want 10,000 tables to have to look up the probability based on degrees of freedom for all of our information every time. So instead of showing us the probabilities for every value of t the way they showed it for every value of z, they instead show us the t-value that's associated with a few different levels of probability. So what we do here is we have a look along the top row for our alpha level. Now remember, we've set alpha at 0.05, but you can see in the title of this table that it says upper level probability, and that means that it's only giving you the positive values for t, and it's only doing one side of the distribution. So that means if we're doing a 2-tailed test, we actually have to be looking at alpha equals 0.025. So I find the column that matches alpha equals 0.025, and then I go down to my degrees of freedom, which you remember is 40, and that gives us the number of 2.021. And that's what's called a critical value of t. And what that means is that the probability of getting a t-value of 2.021 is 0.025 or 2.5%. So that means, by definition, any t-value that's greater than 2.021 is going to be less likely than 2.5% and therefore significant. Our t-value, you remember, was 12. So we are definitely above 2.021, and we can reject the null hypothesis and say that we found evidence that kids are performing above chance on a test about birds. So the way we would say that, or expect to read that in the paper, is t at 40 equals 12. That's saying t with the degrees of freedom of 40 equals 12, and then that the probability of finding such a t-value, that's what p there means, is less than 0.05, which was our alpha. We don't have to say two-tailed here because that's the default in these situations. If this were one-tailed, then we would specifically have to say one-tailed. Now, just a quick pause here to talk about something important. Computers are real, which means that in reality, looking up a critical t on a t-table is, not to put too fine a point on it, a waste of time. Computers now automatically just spit out the probability alongside the t-value. And because they don't have to worry about conserving space, they can give us the exact probability. So I ran my actual data through SPSS, and I got t at 40 equals 12.23. That's just a rounding error. And then the probability is actually much lower than 0.05. It's actually so low that it's virtually unmeasurable. So in that case, we would say p is less than 0.001. So when you read papers that have been written in the past 20 years or so, and if you guys go on to do a quantitative thesis, then you should absolutely have a proper p-value to 3 decimal places and none of this less than 0.05 stuff. And on a related note, as we go through all these tests, I do genuinely think that the practice of doing these calculations by hand can help us really understand what these tests are doing and how they work and the meaning of them. So I think working through step 4 with hand calculations, or Excel calculations even, is a worthwhile endeavor. But to be honest, looking up things in tables is not super helpful. So once we decided to do calculations by hand, it was the only option. You have to use tables in that scenario, but if you're finding the table part specifically confusing, then spend no time worrying about that. That's not something that I would be overly concerned about going forward. It's like not knowing how to churn butter. You'll be okay. Just go buy some butter. If you can follow the steps enough to get through the decision section and understand what two-tailed means and what alpha means and things like that, then honestly, I'm fine. You're fine. Table-wise, we're all fine. But we're not quite done yet. As we discussed in hypothesis testing, significance level doesn't really mean anything. If it's significant, it's significant, and we don't really consider concepts like very significant to be a thing, nothing like that. So instead, what we have to do is look at the effect size, which is a much better measure of the magnitude of an effect. So I mentioned before that we use different effect sizes for different types of data, and the good news is that as we choose a statistical test, we also choose the effect size, by which I mean effect size is also chosen by the nature of our variables and how many groups we have. And when we make the decisions that lead to a t-test, those exact decisions lead to an effect size measure called Cohen's d. And the other good news is that Cohen's d is super easy to calculate. The top part is exactly the same as the t-test, as you can see, and then we just put it over the standard deviation of the sample as opposed to the standard error. So if we did that for our little example, we get d equals 1.87, which is great. Okay, so what does that mean? Well, hopefully you remember that what statistical tests are doing is saying whether our sample came from the same population that would be indicated by the null hypothesis. If we're able to reject the null hypothesis, we're saying that our sample came from a different population. What D does is says how close those two populations would be. It's the difference in units of standard deviation between your two populations. So in this illustration, the blue curve would be the null hypothesis population curve, and the pink curve would be the theoretical population that our sample came from. So D, as you can see, is the distance between those means in number of standard deviations. So for our particular example of D of 1.87 means that our population mean is about 1.87 standard deviations higher than the null hypothesis population mean. So is that a lot? Well, yeah, actually that is quite big. Here are the typical conventions of what is generally considered appropriate in terms of sample size. Small is 0.2, medium is 0.5, large is 0.8. So 1.87 is very big. That's a very large effect size. But remember that an important caveat to this is that a lot of this depends on context. Different areas of study may have different conventions. So, say for example, and I'm making this up, this is not a real example, brushing your teeth had only a small effect size on the number of cavities over a lifetime. But brushing your teeth is a really easy and relatively cheap thing to do, whereas cavities can be painful, distracting, and lead to larger health concerns if they're not treated. And if you do treat them, they can be very expensive to treat. So even if it only makes a small difference, even if the effect size was, say, one cavity over your lifetime is reduced, you might find that brushing your teeth is still worthwhile. The context really, really matters with effect sizes. So even sometimes effect sizes that are small, if the difference they make is a big enough difference that we feel like it's worthwhile in our lives, that's really what effect size means. And so these are conventions, and when we talk about it in research papers and people say, oh, it was a large effect or whatever, they're usually referring to these conventions. But it's always worthwhile to really think about what that means in the context of the study and theoretically how that applies. Okay, so that was the one sample t-test, which we use when we know the population mean. Okay, so now we're going to talk about the scenario where we don't know anything about the population, but we still have two groups, so we're still going to do t-tests because
T for two, and two for tea.
T is always for two. So let's look at this. Now, when we moved from the Z to the one sample t, the big change was using the sample standard deviation to estimate the population standard deviation. That was what gave us the t distribution. But what about when we don't know the population mean either? We can't use the sample mean as an estimate of the population mean because our whole strategy here is saying that the means are different. So we need another mean that's going to represent the population of the null hypothesis. And we do that by collecting a whole other set of data to stand in for the population data and give us an estimate of what we would expect if our null hypothesis were true. So there are two main ways to do that. You can collect a whole separate group of data. The prototypical version of this is the treatment and control group. So you collect data on a group that doesn't get the treatment or intervention or drug or whatever, and so you can see what typical results look like. The control group serves as an estimate of the known population. You can then also, in quasi-experimental studies, have two groups that aren't assigned as treatment and control, but which represent potentially two different groups or two different populations. A good example of this is the Iyengar and Lepper study from a couple of weeks ago. They compared choice preferences between Anglo-American and Asian American students. In that case, they were using Anglo-American students as a stand-in for the population and then comparing whether Asian American students came from that same population. Any study that compares gender is also fundamentally using the same strategy. Now, as a note here, there's an argument to be made that when you do comparisons like this, because it automatically puts one group in the position of being the default or the norm, because we're using it sort of as a substitute for population numbers, and that's a really reasonable point that we're just gonna gloss right over. So as you'll see when we get to the calculations part, we avoid that in a number of ways. We don't treat it mathematically as a population. Mathematically it makes no difference at all, but theoretically it's something that people tend not to like, so it's something to be aware of. Now, the other way you can create an estimate of the population mean is to collect two related groups of data. The prototypical version of this is when you test someone before and after an intervention. So before an intervention, students got X on a test. After an intervention, they got Y. And then if Y is significantly different from X, we'd say they learned something. They're no longer part of that initial population. Another way you can do that is to collect related pairs of people. So a place where this is used a lot is areas where collecting samples is relatively difficult or where variability in individuals is a challenge. So people who study exceptionalities, for example, tend to use this a lot. So as just an example, if you're interested in students who are deaf or hard of hearing, you may have to collect students in many different locations in order to get a reasonably sized sample. But then you don't just want to collect a random hearing sample from Thunder Bay as their comparison group. You want them to have the same features as the deaf sample. So you may say, for example, that for every deaf or hard of hearing person you recruit, you'd recruit a hearing person from that same school and grade. And that way you narrow the differences in your group. You make them more similar. So you account for some nuisance variables that way is essentially what you're doing. Now that means that even though you have two different groups, a deaf group and a hearing group, they're not independent. You've selected your hearing group specifically to be related to your deaf group. I'll talk more about that when we get more to that t-test, but that's basically the principle of the idea. And then the overall point here is that we're estimating the population mean, and there are two basic ways to do it: with an unrelated or independent sample, and with a related or dependent sample. Now, which one of those two ways we choose is actually going to impact which specific t-test we use. So we're going to need to update our little chart here to include the different options, like this. And first we're going to look at the unrelated option, the independent t-test. So the independent t is for any situation where you have two unrelated groups that you want to compare. It's also sometimes called the between subjects design because you have different people in each group, and an unrelated subjects design because the subjects are unrelated. It could also be called, of course, an independent subjects design because the data points are independent of one another. What you call it doesn't really matter. This is just in case you see different terminology out and about. They're all talking about the same thing. Now, theoretically, what we're doing is using the control group or comparison group as a stand-in for the population. But mathematically, you can't just take another sample, say it's the population, and call it a day. Each of those samples is vulnerable to sampling error, and we need to account for that, whether it's the treatment group or the control group. So what we do here is, instead of using the standard sampling distribution of means that we talked about in probability, we're going to use the sampling distribution of differences between means, which means that all the potential differences between any two samples of a certain size drawn from a population. Now, the good news is sampling distributions of the difference between means operate pretty much the same as sampling distributions of means. The shape is still most likely to be normal, and the mean, rather than being the population mean, is going to be zero, as in there's no difference between means. The only tricky bit here is the standard deviation of the sampling distribution, which is the population variance for each sample divided by the sample size and then the square root of the whole thing. I know that sounds confusing. More on that in a second. So this is the conceptual formula, and you can see the top part is pretty straightforward. We take one of our sample means and then subtract the other sample mean. And you can see here that it's the same as the one sample formula, except it's two samples instead of a sample and population. The trickier bit is the bottom part. We need that standard error, which you remember the standard error is a standard deviation of the sampling distribution. So since we're using this sampling distribution of the difference between means, our standard error is a little different than we're used to seeing it. It's the population variance for each sample divided by the sample size and then the square root of the whole thing. But what does that mean? Well, one thing that just sort of works out nicely is that the variance of the difference between means is actually the same as summing the two variances. That's called the variance sum law. So what we're actually going to do, rather than manipulate our standard deviations, is we're going to work with variances, which, remember, the variance is just the standard deviation squared. So in fact, if you already went to the trouble of hand calculating your standard deviation, then you got the variance before you took the square root of it. But we're going to go back to the variance, and we're essentially just going to add them and then divide by the sample size and then take the square root of the whole thing. And that'll give us back to the standard deviation for the sampling distribution of the difference between means, or, your standard error. Except actually it's not that easy, because of course the whole point of this is that we don't have the population variance or standard deviation. So again, we have to estimate our two variances from the samples. And this gets extra tricky because there are two big factors that are going to impact how well we're estimating those population variances, and that's going to be whether the sample sizes are equal and whether the variances are approximately equal. Now, the way you tell if your sample size is equal is if there's any difference. You just look at the numbers and be like, yeah, those are different. But the way you tell that variances is different is a little mushier, because they can be a little bit different but still functionally the same. So hilariously, the answer is actually you have to do a whole other test to see if the differences in your variances are statistically significant. And that is something, of course, on your computer that takes less than a second to do, and that actually comes automatically anytime you do an independent samples t-test. But we don't have that option, so we're just going to default to assuming they're similar unless it really seems different, in which case I'll just tell you it's different. But we are going to talk about in all the different scenarios of whether your sample sizes are equal. And when I say equal sample sizes, I mean between your two groups, obviously. Whether your sample sizes are equal and whether your variances are equal, how that's going to impact how we're going to estimate the standard deviation. So in the first option, we have the same sample size, so both our treatment and control groups have the same number of people in them, and then they have approximately equal variances. In the second option, we could have different sample sizes but still approximately equal variances. Or we could have equal sample sizes but different variances. And if we have then finally we can have different sample sizes and different variances. The most straightforward scenario is that we work out the variance, remember this is going to be the sample variance, for each group and then divide by the sample size for each group. So essentially, when our sample sizes are equal and our variances are equal enough, we just straightforwardly plug in the sample variance for where we had the population variance before. So then when we work out our t-value, that standard deviation equation just gets, or its standard error equation, just gets popped in the bottom here, and then we can work the whole thing out, no problem. If we don't have equal sample sizes, but our variances are equal, then it's a little more complicated. We can't just add them together like we did before, because now they're coming from different sampling distributions. Essentially, a sampling distribution of n equals 20 versus a sampling distribution of n equals 25 are not going to have the same expected variances. So we can still work with that, but we have to adjust it. So what we do here is we average or pool our two sample variances using a procedure that allows the bigger sample to carry more weight in determining the final value. Effectively, we're accounting for the degrees of freedom in our variance through this creation of the pooled variance. So the way we do that is we multiply each variance by its own degrees of freedom before we add them, and then divide the whole thing by the total degrees of freedom. Remember here that each degrees of freedom term is going to be n minus 1. So if our two sample sizes were 20 and 25, our two degrees of freedom would be 19 and 24. And then to get the standard error, we would take the pooled variance and put it over each sample size and take the root. So then again, when we go to work out the t-value, that standard error equation just gets popped on the bottom here, and we can work it out. Now, in the situation where you have the same sample size but unequal variances, we actually go back to the original version where we add them up and divide by n. So then when we go to work out the t-value, that standard error equation again just gets popped in the bottom here, and we work it out again. Now, in this case, because we have unequal variances, we actually do have to adjust our degrees of freedom when we determine significance. So we go back to the original baseline version here, and then we would make adjustments for the unequal variance later on. And in fact, to be honest, you can't actually make those adjustments by hand. You have to manipulate the degrees of freedom in such a way that's too complicated for us to do. So you do it using a computer program. So that's why we're sort of just going to assume equal variances for our purposes here. And then finally, we have the scenario in which you have unequal sample sizes and unequal variances. And the answer to that is that you don't do it. If you have that situation, you get yourself another test, because the t-test is not for you. There are some non-parametric tests that can solve this problem, so you'd move on to them, but we're not really going to talk about them in this course. It's another story for another course. But the idea is if you have unequal sample sizes, you need to use the pooled variance. The pooled variance cannot handle unequal variances, even if you account for the degrees of freedom later on. So we can't do it. We're stuck. End of story. So to sum up, if we're calculating t by hand for an independent t-test, this is how we do it, choosing the correct standard error based on sample size and similarity of the variance. And then, of course, once we have our t, we'd go and look it up in a table, same as we did before. And the only trick here is that our degrees of freedom are actually going to be df1 plus df2. So it's going to be n minus 1 plus n minus 2, or our total n minus 2. So it's just to remember it's not exactly n minus 1 here, although it also sort of is. Okay, we are going to work through an example, but first let's talk a little more about this idea that there are some situations where you just can't do a t-test. This is what's called assumptions for the t-test. So these things have to be true for t-tests to work properly, or have to be true-ish, anyway. The first one is the one we just talked about. Each sample has to have roughly the same variance. This is called homogeneity of the variance. And if your variances are different, we'd call that heterogeneity of the variance. Just two of the many fun phrases we get to use in statistics. It's relatively serious, but as long as your samples are the same size, we've actually developed a way to deal with it pretty effectively. And then the second thing is that the sample data come from a population with a normal distribution, or that your sample data is normally distributed. Now, in actuality, you don't have to worry too much about this one. It doesn't make as big of a difference as the others, so researchers will frequently just ignore this assumption, and that's sort of okay. What we say is that the t-test is robust to violations of normality. The scaling assumption means that your dependent variable has to be on an interval or a ratio scale. And that's another one that's a little more serious than normality, but is also often ignored. People use t-tests with something like a Likert scale, which is really more ordinal than anything, very often. It's sketchy, but it's usually okay, especially if they're adding up a bunch of questions. So this one's really more of a question mark. You should worry about it, but maybe not that much. And then the last one is called independence of observations, and it means that your two groups are accidentally related. And this is a big one. Do not pass go, do not collect $200. You cannot do an independent t-test if your observations are related. And that means related within groups as well. So, for example, if you had two classrooms and you assigned one to the treatment group and one to the control group, that's a recipe for problems. You genuinely have to work hard to make sure your observations are independent, and assigning classrooms, assigning treatment and control versus at the classroom level instead of at the individual level is a good way to invite problems. Okay, let's work through an example. So in this study, we're going to see whether kids who hear a story about a familiar topic learn more words from that story than kids who hear a story about a novel topic. So running through the steps of hypothesis testing, I have this research question, as you can see. I have a sample, the same sample of kids, the same sample of 41 kids, but they're assigned to two different groups. The null hypothesis is that there's no difference between those two groups. And you can see the means and standard deviations for each of the groups there. Okay, then, so since we have unequal sample sizes and equal variances, we're going to use the t formula that includes the pooled variance, which means we're going to have to calculate the pooled variance, which you can see here, but I have as equaling 0.08. Okay, so then we can take that, plug everything into the t formula, and hopefully you also get t equals 0.57. So now that we have our t value, let's look up the critical value in the t-table, same as we did before. And again, we're going to have our alpha at 0.05 in a two-tailed test, so we're going to look in the 0.025 column. And then our degrees of freedom is n-1 plus n-1, so that's going to be 19 plus 20, so 39. And that brings us to, this t-table doesn't include an option for degrees of freedom of 39. So what do? Well, we have a few options. The easiest is we go to the one higher. In this case, degrees of freedom equals 40. The higher the degrees of freedom, the lower the critical t. Essentially, the more participants we have, the better we're estimating our population, so the easier the criteria are. So we look at the higher one, and if we're not significant there, then we're never going to be significant. As you can see, the critical t for 40 is 2.021, and our score of 55 is way lower than that. So we can confidently say that we failed to reject the null hypothesis. Now, if it was significant here, then what we would do is we'd check the lower one, and if it was also significant there, then we could confidently say we reject the null hypothesis, because if it's significant at both of them, and when it's supposed to be in between, then that says it's significant overall. And if it was in between, so it was significant when you're looking at 40, but not significant when you're looking at 30, then we just go find a computer. That's too much effort to start dicking around with tables there. We would just stop looking at that point. But there are ways you can work it out. And then from there we can calculate effect size. Now, even calculating this is a little shady, since we already failed to reject the null hypothesis. So to begin with, we don't have any evidence that this is a different population from the null hypothesis population. But just for the purposes of illustration, here's what we would do if it was significant. Again, we're using D, which operates basically the same way. The formula is just a tiny bit different. We're taking our the difference between our two means and putting it over the pooled standard deviation. And so before we found the pooled variance was 0.08. So remember, we need to take the root of that to make it a standard deviation. And then when we plug everything in, we get an effect size of about 0.18. So no surprise here, that's a really small effect for a non-significant finding. Yay! Phew, okay, so that's the unrelated sample. Let's now take a look at what happens when we have dependent or related samples. So when you have related samples, then what you have is what's often called a within subjects design. That's when you have data from, or when data are obtained from the same or related samples of individuals. And it's also called sometimes the dependent samples, related samples, repeated samples, or repeated measures. And again, the terminology doesn't matter. They're all referring to the same thing. Oh, paired samples. That's another one that you sometimes call it. And as we mentioned before, there's a couple of ways you can do that. Either a single sample of individuals is measured more than once on the same dependent variable or related dependent variables, or the same, in other words, the same subjects are used in all of the treatment conditions, or it involves two separate samples, but each individual in one sample is matched with a subject with an individual in the other sample. So the matching is done so that the two individuals are equivalent nearly with respect to specific variables that the researcher would like to control. So it's usually things like age, gender, race, etc. So it's really more about making sure that people are similar in some way, that they're matched or paired in some way, is what you're doing when you're doing a matched subject study. Most commonly, though, you see it as a repeated measure study, or a study where participants are in every group of the treatment group or every comparison group. Now again, theoretically, what we're doing is we're using the baseline score, whether that's a pretest or a matched participant or a comparison time, to stand in for the population. But still, mathematically, that's not a thing you can do. We still have to account for any of the errors we have because these are still samples. And the way we do that is by examining the differences as though they were change scores. But this time, because we're not pulling two independent samples, our sampling distribution is actually going to be of mean difference scores. Here's what that means. Essentially, what we do when we use a within samples or related samples t is that we take each match score and subtract one from the other. In this example here, they tested people before and after a training, and then for each participant, they've calculated the difference from time 1 to time 2. That's what that last column is. And that difference score in that last column becomes the new data set. Our sampling distribution is the distribution of mean difference scores for samples this size. Essentially, like we did for Z and like we did for one sample T, this difference score becomes our data. So then the sampling distribution of mean difference scores is the sampling distribution we're going to be using here. Fortunately, again, all sampling distributions are pretty much the same, so the shape is still most likely to be normal, and the mean again is going to be 0, as in there's no difference between the matched scores. And in this case, the standard deviation is actually more intuitive, I think, and it's actually the standard deviation of the population difference score over root n. So remember, our sample data here for this kind of dependent design is the difference scores, and that's identified by the letter D. So the top of our T formula here, remember, we're going to treat our difference scores like regular scores, so it's D minus the population of the D mean, which from the sampling distribution we know is always going to be 0. So we can actually go ahead and drop that. So this is our more practical formula. It's the mean of the difference scores over the standard error for the difference scores. And then in order to get that standard error at the bottom, we are going to have to use the standard deviation of the sampling distribution, which is the population difference standard deviation over root n. But since we don't have that, of course, we're going to estimate it using the sample difference standard deviation, same as we've been doing all along. So just like before, we had to calculate the standard deviation for each sample, we're now going to calculate the standard deviation of those difference scores. Essentially, we're treating those difference scores as though this were a one sample T. I really can't emphasize enough how much all we're doing is using the difference scores as though they were one sample scores. All of this should feel very familiar from like half an hour ago to you. So that brings us to our T formula, which we can use pretty straightforwardly. Okay, so that's easy enough. Let's work through an example. This time we want to see how kids learning English learn words from TV. And we're interested in how the different ways shows can present words can impact student learning. So specifically, we're going to look at whether the show uses visual effects to highlight a word. So for example, say they say like, look at the caterpillar, and then there's a zoom in on a caterpillar and it glows or whatever. Or they're using definitions, so they'd explicitly say something like, a hurricane is a very big storm with lots of wind and rain. Okay, they give a definition. So we showed 22 ELL students both sets of shows, and then we test their knowledge of those words. So this isn't a pre-test and a post-test, but each person got both versions of the treatment, so to speak. So that means it's still a related samples or within subjects design or a dependent design, whatever you want to call it. And then, of course, in step 3, the null hypothesis is, of course, that the difference score will be 0. Now, I've put the means for each category in here, but of course we can't do anything with just the means. For a related t-test, we need the raw data. So here it is. As you can see, we have their scores in each column and then a column with the difference. And then once we have that column with the difference, we can calculate the mean and standard deviation of that column. You'll see that the mean here is actually a negative, and that's just because of the way I decided to subtract visual from definition. That honestly doesn't even mean anything. Okay, so let's go ahead and apply the t formula to that data. And hopefully you all got also that t equals negative 2.21. Now, t is a metric that has essentially absolute value. That's why it didn't matter whether I did definition minus visual effects or visual effects minus definition. We get which A of the 10 we're looking at from the overall means when we go back and look at that. So I encourage you to spend zero time worrying about whether it's negative or not. If you even forget to transfer over that negative, no worries. The value of t is an absolute value number. Whether it's positive or negative does not matter. So now that we have our t value, let's revisit our old friend here, the t-table. And we're going to, as usual, do a two-tailed test with an alpha of 0.05. So we'll be looking in the 0.025 column. And then our degrees of freedom for a dependent t is n minus 1. And since we had 22 participants, that means our n is 21. So let's find that, or our degrees of freedom is 21. So let's find that. Okay, so we find a critical value of 2.08. Our t-value, 2.21, is higher than that, so we can go ahead and reject the null hypothesis. And again, here's how you would write that. We don't need the negative because t-values don't care. And again, computers are real, so we wouldn't actually write it like this. We would write it like the second option here, where we list the specific p-value to 3 decimal places. Okay, and then as with the other groups, the main effect size we use for dependent t is Cohen's d. Unfortunately, the formula we used before for Cohen's d doesn't work for within subjects because it, like the independent t, assumes that the data is independent. So we need to account for the correlation between our two variables in order to get a meaningful value of d. And that's a little too complicated for the level that we're at here. So there are several free online calculators, and you would just sort of pop that information into there, and that will make that life much easier. Now, of course, to use those online calculators, you would still need to find the correlation between our two measures, which is a process we will talk about on another day. So for now, we're just going to ignore effect sizes for related samples. And that's it. That's the gist of how we compare groups when we have 2 of them. So I will see you around. Thanks. Bye.